Hello everyone. Today we are going to learn about real numbers. Yes, of course, we know about various kinds of number systems like real numbers, integers, natural numbers, whole numbers, etc. We know that among all these number systems, so far we know the biggest number system is real numbers. Today we are going to learn some of the basic properties and characteristics of real numbers. So we shall begin. To begin with, we are going to define a lemma, Euclid's lemma, because Euclid's lemma is one of the most important lemma which states one of the most important property of real numbers. So we can define Euclid's lemma. Euclid's lemma. Euclid's lemma is a lemma which defines a relationship between any two positive integers. So to define Euclid's lemma, to state Euclid's lemma, we must need two integers basically. Let a and b be the two arbitrary integers. So here a and b are two arbitrary integers, positive integers. Let a and b be two positive integers. Then Euclid's lemma states that there exist unique integers. There exist unique integers q and r such that a is equal to bq plus r, where 0 less than or equal to r less than b. So Euclid's lemma states that whenever we are provided with two integers, let a and b can be any integers. So these are two arbitrary positive integers. If we are given with two arbitrary positive integers, we can represent the bigger integer, say a, in terms of b like this: a is equal to bq plus r, where the variation of r is given by 0 less than or equal to r less than b. Of course, you may feel confused on hearing this definition all at once. So we can understand this definition in simpler terms just by understanding it with the help of some examples. We shall check this Euclid's lemma with the help of some examples like this. Say a is equal to 51 and b is equal to 5. Then in order to represent a in terms of b just like this, it is enough for us to divide the bigger integer a with the smaller integer b. So in dividing 51 by 5, we get 10 times 5 equal to 50 and the remainder will be 1. So we can represent 51 as 10 into 5 plus 1. So we are provided with two integers a and b like this, and we are able to find another two integers in order to represent 51 in like this. 51 is equal to 10 into 5 plus 1, bq plus r. See, r is equal to 1 here and q is equal to 10 here, and r, the variation of r is 0 less than or equal to r less than b. Here r is 1, which is less than 5. Of course it is valid. We can check another example also. Let a is equal to 101 and b is equal to 20. Then in order to verify Euclid's lemma, it is enough for us to divide the bigger integer by the smaller integer. We shall check it. 101 divided by 20. 25 times equal to 100 and the remainder will be 1. Hence we can represent 101 as 101 is equal to 20 into 5 plus 1. See, here also we are able to represent the bigger integer 101 in terms of the smaller integer like this. 101 equal to 20 into 5 plus 1. See, here we got q as 5 and r as 1. Here also 1 is less than 20. The condition is satisfied. This is Euclid's division lemma. So now we know what is Euclid's division lemma. That is, for any two arbitrary integers a and b, we can find unique integers. Note that unique integers q and r such that a is equal to bq plus r, and the variation of r can be varied from 0 to the divisor b. Now, what is the use of Euclid's division lemma? One of the most important use of Euclid's division lemma is that we can find the HCF of any two arbitrary integers. Say, if we are provided with two integers a and b, we can easily find the highest common factor of a and b using Euclid's division lemma. Now, my question is how we are able to do this, or how we can find the highest common factor. The answer is simple. We can use Euclid's division algorithm. Let me explain how. Euclid's division algorithm is an algorithm used to find Euclid's highest common factor of any two integers. See, I have listed several steps here. By using these steps, we can find the highest common factor of any two integers. Step 1 states that if we are asked to find the highest common factor of two integers, say a and b, then the first step states that apply Euclid's lemma to a and b to represent a is equal to bq plus r. The first step in finding the highest common factor of any two integers is that represent those two integers in the form of a is equal to bq plus r using Euclid's division lemma. Now, the second step, if r is equal to 0, in this representation, if r is equal to 0, then highest common factor of a and b is nothing but the divisor b. Now, the third step gives if r not equal to 0. If r not equal to 0, we have to apply Euclid's lemma to b and r. That is, we have to apply Euclid's lemma to b and r. If r not equal to 0, we shall apply Euclid's lemma to b and r. Then the step 4. Continue step 3 until r is equal to 0. We should continue this process until the remainder becomes 0. In that case, when the remainder becomes 0, the divisor at that stage will be the highest common factor of a and b. So, whenever in the process of representing any two integers in the form of a is equal to bq plus r, we get r is equal to 0 or the remainder is equal to 0, the highest common factor of those two integers will be the divisor at that stage. We shall apply the Euclid's division algorithm to some integers to understand this algorithm better. Now let us apply Euclid's division algorithm to the integers a is equal to 455 and b is equal to 42. Since a is the bigger number, we shall express a in terms of b. How? By Euclid's lemma, we should find the quotient and remainder when we divide 455 by 42. 42 is contained 10 times in 455, so we get 420 and the remainder will be 35. Hence, by Euclid's division lemma, we are able to represent 455 in terms of 42 like this. 455 is equal to 42 into 10 plus 35. See, the remainder here is 35 and it is not equal to 0. So, we should continue our process. In step 3, if r not equal to 0, apply Euclid's lemma to b and r. Here b is equal to 42 and 35. So, in order to find the HCF of 455 and 42, we should repeat the process with b is equal to 42 and r is equal to 35. So, now our new integers are 42 42 and 35. Apply Euclid's division lemma to 42 and 35. 35 is contained one time in 42. So we get 35 and the remainder is 7. So we can represent 42 is equal to 35 into 7. 35 into quotient 1. 35 into 1 plus 7. Here also the remainder is not 0. See, remainder equal to 7. So we should again repeat the process to find the HCF. Here the divisor equal to 35 and the new remainder equal to 7. So we should repeat our process with this divisor and this remainder. In order to apply Euclid's division lemma, again we are dividing 35 by 7. 7 is contained 5 times in 35. We get 5 into 7 equal to 35 and the remainder is equal to 0. So we can express 35 is equal to 7 into 5 plus 0. See, remainder became 0. And in this case, we can conclude that the divisor at this stage will be the HCF of A and B. The divisor at this stage is 7. So we can conclude that HCF of 455 and 42 is equal to nothing but 7. Now we shall move into the illustrative examples. The first example, find the HCF of 225 and 135. Now we know that in order to find HCF of any two numbers, it is enough to apply Euclid's division algorithm. How we can apply Euclid's division algorithm? See, the two numbers are 225 and 135. The very first step is to identify the bigger number. Here, the bigger number is nothing but 225. So, the first step of Euclid's division algorithm is to represent the bigger number in terms of the smaller number by Euclid's division lemma. How we can apply it? We shall divide the bigger number 225 by 135. 135 is contained one time. 135 and the remainder is nothing but 90. So we get 225 can be represented as 225 is equal to 135 into 1 plus 90. Here 90 not equal to 0. R is not equal to 0. So we should apply Euclid's division lemma again to 135 and 90. 135 divided by 90. 1 time 90 equal to, the remainder will be equal to 45. Hence we can represent 135 is equal to 90 into 1 plus the remainder equal to 45. See, 45 also not equal to 0. So in order to find the HCF of these two numbers, we should apply Euclid's division lemma again to 90 and 45. Always remember that we should apply Euclid's division lemma again and again to the divisor and the remainder until we get the remainder equal to 0. Here the remainder is not equal to 0. Hence we should apply Euclid's division lemma again. So 90 divided by 45. 45 is contained 2 times. So we get 90 and the remainder is equal to 0. So we can represent 90 is equal to 45 into 2 plus 0. So the remainder in this stage equal to 0. Hence we can conclude that HCF of 225 and 135 is nothing but 45. So we get HCF of 225 and 135 equal to 45. Now we shall move into the next question. Show that any positive odd integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5 where q is some integer. So we should prove the representation of any positive odd integer is in one of the form 6q plus 1 or 6q plus 3 or 6q plus 5. So how we can prove this? We know that by Euclid's division lemma, we can represent any integer a in the form of bq plus r, right? Here bq plus r, see 6q plus 1, 6q plus 3, 6q plus 5. From this comparison, it is clear that b is equal to 6 in this question. Now let a be any integer, any positive odd or even, let it be a be any integer and b is equal to 6. Then by Euclid's division lemma, we can represent a is equal to 6q plus r, where 0 less than or equal to r less than 6. Since in Euclid's division lemma, the variation of r is from 0 less than or equal to r less than b, and b is equal to 6 in this case, right? So we get a is equal to 6q plus r, and the variation of r is like that. That is, a can be 6q plus 0, or a can be 6q plus 1, a can be 6q plus 2, or a equal to 6q plus 3, or a is equal to 6q plus 4, or a is equal to 6q plus 5. Here 0 to 5 is the variation, since r is strictly less than 6 in the definition of Euclid's division lemma. So we get a can be represented in one of these forms if a is any integer. Now our question is, a is a positive odd integer. See, a is equal to 6q. 6 is an even number, and whatever q be, an even number multiplied by an odd number or an even number will be resulting in an even number. So it is an even number, so a is not odd number here. In 6q plus 1, it will be definitely an odd number, a odd number, because 6 is even, q is any number. Then 6q will be even number, 6q plus 1 will be odd number. So any positive odd integer can be represented in this form. Okay. Now 6q plus 2, 6q is even and 2 is even, so it is also an even number. Now 6q is even, 3 is odd, and 6q plus 3 will be odd number. 6q is even, 4 is even, so the sum will be even, so it is not an odd number. Similarly 6q is even and 5 is odd, so the sum will be an odd number. So in this 6 representation, only 3 of them will be odd numbers. So it is clear that if a is any positive integer, we can represent a in only of one of the form of 6q plus 1 or 6q plus 3 or 6q plus 5, since other 3 forms are forms of even numbers. Is it clear? So we can move to the next question. The example 3. The question is, an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So here 616 members has to march behind a band of 32 members, and the number of columns each group should form must be equal. How we can find this? Since 32 members has to divide into certain columns, the number of columns must be a factor of 32. Okay. Since 616 members has to form columns, the number of columns will also be a factor of 616. Since both the bands, both the groups should have same number of columns, the factors must be common and it should be the maximum. So we should find the highest common factor of 616 and 32. Now how we can find this? The highest common factor of 616 and 32 can be found out by using Euclid's division lemma. So I hope now you can work it out by yourself, and please comment the answers in the comment section if you can figure it out. We will check it and verify it, and please also post your doubts if any in the comment section. Also follow us on Instagram to have detailed clarifications on any doubt, and we will post or upload videos regarding that. Thank you.